The model is for a heterozygous individual, meaning they have one sickle cell gene for hemoglobin and one normal gene for hemoglobin. The normal one is the white, and then, as you know, the sickle cell one is the gray. The restriction enzyme finds the DNA sequence only in the mutated gene. The normal gene doesn't have the mutation, so the restriction enzyme simply can't find the DNA sequence that it's used to looking for. And so, therefore, the normal one never gets cut. You now have three chunks of DNA. All three strands of DNA are different sizes. We need to be able to see those, and that's where gel electrophoresis comes in handy. So I'm drawing the wells. You will draw three wells at the top of your whiteboard. The first well is where you're going to load your heterozygous model. So again, we have three different size DNA chunks because the restriction enzyme was able to cut at least one of them. The smallest guy is going to be able to move across the gel the furthest. So the smallest fragment of DNA has the least number of base pairs and can travel the furthest. Then you're going to want to find the second largest or the second smallest, and that one will travel not nearly as far as the little short guy, but it will travel across the gel further than the one that was never cut. So here you have the smallest, the second smallest, and then the normal gene that never got cut. That is a lot of DNA. It won't travel very far at all. This is now called a lane. This is lane one, well one, lane one. Your job will be to determine what lane 2 and 3 will look like. So, lane 2, you will load DNA that has two normal hemoglobin genes. So, that's hemoglobin normal times 2. That's homozygous. In lane 3, you will load DNA that is sickle cell. Both genes are sickle cell mutated, also homozygous. So this is what your whiteboard should look like, 3 bands in lane 1, and then you can draw what the band pattern will look like in lanes 2 and 3.